In metrology, major discoveries often bear the names of important scientists. This is precisely so in the case of flow metering by means of the Coriolis principle. Born in 1792, the French mathematician and physicist Gustave Gaspard de Coriolis was the first to describe the force that history has named after him. At that time, he would not have guessed that 200 years later, his discovery would form the basis for one of the most important principles employed in the world of industrial metrology and process control.
A body in a rotating system experiences a sideways deflection. The stream of water is being deflected sideways, but that has nothing to do with a centrifugal force. It is a different force, the Coriolis force.
As you can see, our perception of straight-ahead movement in a rotating system is not at all what we would have expected. As far as the observer inside this system is concerned, it appears that something is pushing the moving body sideways. This is the perceived effect of the Coriolis force. A movable rubber tube, let's pretend that it's the metering tube of a Coriolis flow meter, is set in motion by an external force that causes it to swing back and forth. The tube is filled with water, but the water is motionless. In other words, it is not flowing. Not yet, at least. Under these conditions, the tube swings back and forth in a uniform and smooth pendulum action. Once the water starts flowing through the tube, however, the Coriolis forces cause the tube to take on a clearly perceptible lateral swinging action about its own axis. The intensity of this swing, or phase offset as it is also known, is measurable. It is directly dependent on the rate of mass flow. The more water that flows through the rubber tube, the more intense the swing becomes. This is information used in directly calculating the rate of mass flow through a piping system. As soon as the flow of water is shut off, the apparatus settles back to its normal, smooth pendulum action. The swinging action of Coriolis metering tubes is known as oscillation, and it can be simulated by mathematical models on the computer. As soon as a fluid starts flowing through the oscillating metering tubes, Coriolis forces kick in immediately, significantly modifying the geometry of the pendulum action and introducing a superimposed oscillatory movement. This simulation underscores the effect of the Coriolis forces. Here are the metering tubes in action, initially without a flowing fluid. The finite element method, FEM, is one way of visualizing and computing movements, forces, stress, and other variables. This data goes a long way toward optimizing the structure and the design of Coriolis mass flow meters. This example shows a promass meter as an illustration of how electromagnetic exciters cause the metering tubes of Coriolis flow meters to oscillate. The two tubes are oscillating at a frequency of 480 Hz. The amplitude of oscillation is minute, a mere 30,000ths of a millimeter. With a specified deviation of only 0.1%, Coriolis meters register in-pipe flow more accurately than virtually any other type of meter. The requirements that apply to the manufacture of Coriolis meters are correspondingly high. Only cutting-edge production technologies can ensure uniformly high in-process metering quality, day after day, month after month, and year after year.